Okay. All right. Thanks for coming back. So let's carry on from where we were yesterday. Let me give you a brief summary of what we have discussed yesterday, okay, in the first lecture. So what do we have so far? So if we assume spherical symmetry, okay, so let's assume spherical symmetry and then we'll justify. But if we assume spherical symmetry, we can define a function that I call compaction function, which is 2 times the over Misne-Sharp mass divided by the area radius, which is equal to the integral of rho minus rho bar. So now we are in asymptotically Friedmann-Robertson-Walker space-time. So this is the energy density of the background, okay, multiplied by r square r prime dr integrated over a ball that goes from 0 to r divided by r, and I put a 2. Where this area radius, because we are in spherical symmetry, we can take the metric that is explicit spherical, okay, so it is related to the angular Killing vectors, and so the metric looks like this, dot dot dot, whatever it is, r square d omega square, okay, where this r is what we call area radius, and in principle depends on the radius, and time can depend, okay. So in these coordinates, then this function here, which is really the radius of a sphere, is a scalar. Okay, so, and then also, as we saw yesterday, all this object, this integral is also a scalar. So this object here is an observable, okay, because it doesn't change with coordinates. Now, whenever C becomes order 1, then we form trapped horizons. A trapped horizon, and then what happens is that this initial ball of matter collapses into a black hole. Okay, so that's what we said yesterday. Now, second point that we said yesterday is that at formation, black holes has to be a very small number with respect to, has to have very small density with respect to the density of radiation. Why? Because at formation, their energy density, because black holes all interact gravitationally, so the energy density simply dilutes like volume, okay? And the volume in Friedmann-Robertson-Walker space-time is simply the scale factor to the power 3. While the radiation of the universe, because what we are thinking is that those black holes are generated by large inhomogeneities in the radiation epoch, the radiation goes like 1 over a to the 4. So that means that the radiation of black holes divided by the energy density of black hole divided by the energy density of radiation scale like the scale factor, okay, which in terms of e-foldings is e to the n. So that means that even if we start with very small black hole, if we wait few e-foldings, those become exponentially larger, okay? Up to a point in which at the matter radiation equality, we want to have this ratio to be order 1, okay? So the conclusion is that we need to have actually exponentially small number of black hole at formation to have it order 1 today, okay? This fits well with inflation because, well, as we heard in the classes of inflation, what happens is that the infladon generate quantum mechanically perturbations, and those perturbations are in average very small. It's the CMB, 10 to the minus 5, okay? But then, because the infladon produce perturbation quantum mechanically, when classicalized, a superhorizon scale, become a statistical variable. And so there is always a chance, even small, exponentially small, that these fluctuations are way larger than 10 to the minus 5. In fact, they become over 1 and then can collapse into a black hole. Okay? So this fits well with inflation because precisely inflation tells us that this should be a very, very rare event, exponentially small. Okay? So what we said is that, well, then let's connect basically this compaction function with the overdensity generated by inflation. Okay, so that's the idea. And what we said is that, well, at super horizon scale, so let me take a fluctuation that has a wavelength much bigger than 1 over AH, okay, which is super horizon scale. What we showed yesterday is that at least during radiation, which is when we want to form those black holes, at super horizon scale, the metric generically looks like minus dt squared plus scale factor e to the 2 zeta dx dx. Okay, where zeta dot is roughly 0. Okay, so it's like frozen scalar perturbation at super horizon scales. Okay, so this is the metric that we are going to use, because the idea would be, we are going to see that what we want to give is the initial condition for the compaction function such that in later time, this compaction function will become order 1 and will form black holes. Okay, so this initial condition will be given statistically, and in principle will be given to someone that would do simulation of gravitational collapse, for example, and tell us, okay, with this initial condition, you form or not a black hole. Okay, so we know when the black hole is formed, but not, I didn't give you yet the initial condition such that this evolves to that point, which I'm gonna do today. Okay. Now, but before doing that, so let's carry on with this inflation thing, because basically this overdensity will be generated by local curvatures. Okay, zeta is what we call curvature perturbation in this case. Okay. All right. So what we are gonna do, because zeta is only space dependent, and of course decay to 0 at infinity, because at infinity I don't have this perturbation. Okay. So then I can always Fourier transform, and then this is 1 over 2 pi to the cube, the integral of zeta k, those are the Fourier modes, e to the ek x d3k. Okay, so this is simply a Fourier transformation, and what we are going to assume in these classes is that zeta k is a Gaussianly distributed random variable. Okay, so we will not consider cases in which the curvature perturbation is non-Gaussian. Why? Well, first, because it's simpler, and second, because so far in the CMB, for example, we didn't see any non-Gaussianities. So for sure, it can be a working step to start. Okay, so then we can always make it more complicated by introducing a different probability distribution of those curvatures. So those are Gaussian for this course, and then zeta, you can imagine an integral is simply a sum. Okay, so this is called multivariable Gaussian. So multivariate, yes, multivariate Gaussian. Okay, so the zeta is a probability distribution which is multivariate Gaussian. Okay, so, but if this is Gaussian, as you know, Gaussian probability distribution is simply given by two numbers. Okay, the mean value and the variance. Anything else, it's simply related to that. Any higher correlation function are related to these two numbers. Now, the zeta is a very specific, well, it's a Gaussian variable, and as we saw yesterday, well, 2 days ago by now, zeta k is equal to 0, so it's centrally peaked. Okay, so the average, that's why the CMB, if we take it, it's basically homogeneous and isotropic. Okay, because the variance is the zeta k is equal to 0, and the the other thing that we need is the two-point correlation function, which is related to what we call the power spectrum. So we would need zeta k prime, which is equal to, by, let me use the correct normalization here, 2 pi to the cube delta 3 k minus k prime, and this comes from isotropy because this is generated by inflation. And then we have the power spectrum of curvature perturbation, which is the one-dimensionless, so I divide by k to the cube. Okay? So that's the definition of the power spectrum of curvature perturbation, which is the two-point correlation function in Fourier space of our curvature perturbation. Okay, so with that, everything is determined for the statistics, basically, for the statistic of zeta. Okay. Now, the point is this one. We say that the probability distribution is Gaussian. Okay, for any zeta k. Of course, we are interested not in the central region, because we are interested not in this part, which is the small perturbation in average, let's say. We are interested in what happens in the tail of this distribution, okay? Because we want to see some exponentially small rare case, okay? But in any case, even if we are interested in this tail, as we said, the probability distribution is completely determined by the two-point correlation function. Okay? So what we could do is, well, what we need is the variance. And because the variance is dominated by linear perturbation theory, because you can imagine that anything else is exponentially suppressed, so if to calculate the variance, I should integrate from minus infinity to plus infinity, right? But because this is exponentially suppressed, it's enough to calculate up to actually the value of the variance. Why do I'm pointing this out? Because what we can use actually with a very good approximation for this power spectrum is the power spectrum that we calculate from perturbation theory. Okay? Even if we need the full probability distribution, so in principle, we should calculate it also knowing the full theory here in the tail. Okay? It's enough to know what happens in perturbation theory. Okay? Because that's what we are going to use. Okay? So with that, basically we have this object here, which will be given by whatever. For example, 2 days ago we saw this is one way, but if you want to invent something else, in fact, all this approach is still valid, because you simply have to give me a power spectrum at super horizon scale to start with. Okay? Whether this is coming from inflation or something else, of course, is an extra assumption that it goes well with us, because we know inflation, it's predictive, so it already gives us some information about our universe, so we also connect it to primordial black hole. But it's not necessary. Okay? As long as there is a power spectrum of perturbations, then we can start doing our analysis. Okay? All right, but of course, well, here there is a little bit of inflation though, because as I said, this power spectrum is isotropic. Okay, so I'm also giving you a very special two-point correlation function. Okay, this is very special because it's only non-zero when k is equal to k prime. And of course, this is typical of a spin zero particle, let's say. Okay, so it's a massless sorry, not massless, but a scalar field, a spin zero. Okay, and that's why somehow also give us some information that this is related to inflation, because inflation is generated by a scalar field. So it doesn't have any preferred directions. Okay, so it is isotropic. Okay, now on top, we also have an extra information due, if we think about these objects generated by large fluctuations of inflation, which is the following. Again, inflation is generated by a scalar field. Scalar field doesn't have any directions. So if scalar field doesn't have any direction, let's suppose I have an isolated perturbation that is very large. What would be the geometry of this perturbation? What do you think? So I have an isolated large perturbation generated by the scalar field, which is isotropic. Will be spherical, because otherwise if it was not spherical, it would mean that there is a preferred direction. Okay? So how can we get non-sphericity? Well, if I take if I drop a stone in the sea, or in the lake, actually it's better because it's flatter. In the lake, I see that I just get spherical symmetric wave. But if I drop 2 stones, then I start getting something that is not spherically symmetric. Okay? Same thing is for perturbations. So if you take just one isolated perturbation, this will be spherically symmetric. But if you take more, so you take something that is not rare, then you're not gonna get spherical symmetry. Okay? So this is an intuition that we are gonna prove as well. Okay? So the key point now then is that if this intuition is correct, then what happens is that around a very large isolated perturbation, which is the one that would form a black hole, around that perturbation, the space-time is spherically symmetric. Okay? So that's why I started talking everything about spherical symmetry here. Because in fact, for rare perturbation, as we also gonna see statistically, but we already understand physically, perturbation are spherically symmetric. Okay? So what we are interested in is in gravitational collapse of a spherical symmetric object. Okay, is that clear? You understand, no? Physically what happens. So the point is this one, that a scalar field doesn't have any favorite direction. Okay, so that means that the only thing that you can have when you have an isolated perturbation is to be isotropic. Because otherwise it will give you, I mean, you can have only breathing modes if you want. You cannot have a specific direction, because if you would have a specific direction, it would mean that you are kind of breaking spherical symmetry. Well, sorry, we are kind of breaking the fact that the spin is 0, right? Because you can have only a preferred direction if you have a vector. So if you have a vector, then the field itself determines one direction, okay? So by itself, if you have just an object that is large fluctuations that is not perturbed by another large fluctuations, then this is by d per se is spherically symmetric, because it's the minimization of its energy, if you want. It's like why oranges are round, or why planets are round. Because the minimization is really, I mean, somehow there is just the Newtonian potential, which is like the scalar part, if you want, of gravity. And so you don't have any favorite direction. Imagine if you had a planet that is a rugby ball. It's impossible, because otherwise gravity would have some specific direction. Okay. Okay, so then the only way, as I said, to form a aspherical perturbation is that you're considering a perturbation that is not so rare, so it's very close to another one, and then they interfere and will create different objects. Okay, so this is why, for example, in a large-scale structure, when we form galaxy or whatever, they are not spherical. I mean, they also have some shape and whatever. Okay, the halos can have some shapes and whatever, because they are not so isolated. Okay, but here we are really talking about something that is exponentially rare. Okay? So you can really think that is standing alone. Okay, so that's more or less the idea. Okay, so now how do we connect this compaction function with the energy density? Okay, because what we know is the compaction function given an energy density, okay? And then the next step we did is, well, what we know the metric, because we got it from inflation, for example, so we know the curvature perturbation, so I need to connect these two things, okay? So the way we do is, of course, by Einstein equation. Okay, so it's actually the first time until now that Einstein equation appear. Because until now, it's everything just geometrical. Because the compaction factor equal to 1 forming trapped horizon, it's a geometrical thing. Okay. Okay, so then what happens is that we are now, as we say, the super horizon scale where everything, so our gravitational potential, if you want, is zeta and it is time independent. Okay, so what we want to connect the zeta with the energy density, we basically have kind of the generalization of general relativity of the Poisson equation. Okay, so the Poisson equation is simply in linear gravity. It's simply the Laplacian of the gravitational potential equal to the energy density. Okay, and in fact, if you use Einstein equation with that metric that I wrote there, you find that the over density delta rho over rho bar. Okay, this is related via a kind of Poisson equation. The Poisson equation turns out to be, in general relativity, minus 8 divided by 9. I mean, this, you can put it in your favorite Mathematica code, like Mathematica or Maple, if you use whatever, and then you will get this equation. Zeta, here is where the Laplacian comes, okay, Laplacian square, and then here we have an a square h square e to the zeta half. So this is completely non-perturbative. Okay, so the only thing I'm doing here, I'm not doing perturbation theory as we were doing in inflation, where the expansion is for small zeta, but for any wave number. Here we are doing something different. Here, what we are doing is an expansion in small wave number, because we are at super horizon scale, but we don't say anything on the amplitude. So the amplitude, because obviously we want to have a large amplitude for our over density. Okay, so the expansion that we are using, that's why also we are using a super horizon scale to give the initial condition. The expansion we are doing is what is called gradient expansion. Okay, so we are taking the leading order in very large wavelength. Okay. And so that's why there are all these exponentials. So you can see this is completely nonlinear.
Large wavelength, right? This should be very small wavelength. The reason is that
very small wave number, a very large wavelength.
Because, if you look at the 0, 0 equation, there will be other terms involving the body. That is what I'm not able to understand. Because if I had worked in the Newtonian gauge, which you are not working, I know, in the Newtonian gauge, there will be other terms involving phi dot and phi double dot. And if you want to really arrive at something like
in Newtonian gauge, there is an issue that the phi k, it's actually going like 1 over k squared. So what happens is that, for example, as you showed last time, is that you have terms that goes like phi k squared phi k, and you would think that those are negligible. In fact, they are not, because in Newtonian gauge, what happens at super horizon scales, non-perturbatively, they are actually non-local. This is what we call non-local. So it goes like 1 over the Laplacian.
Saying that in that metric,
Newtonian gauge is a very bad gauge for this thing.
Okay. In that metric that you have,
Yeah.
the 0, 0 Einstein's equation will lead to this.
Yes, because you will have two things. So that when I wrote that metric there, I also told you that di beta I is 0. Okay. However, if you go in Newtonian gauge, somehow this is related to this. There are some gauges in which this is not 0 because beta I, it goes like 1 over k squared. And so you have to be careful. So I use a quite generic set of gauges where the shift is equal to 0, but not all of them are. So you can have some gauges, for example, precisely Newtonian gauge, it's where actually this is not true. So you need to consider the shift. And then things, I mean, at the end the result will be the same. So this is, the result is going to be gauge invariant. But you have to be careful on the approximation you're doing. And the approximation I'm doing here, which I put it under the carpet yesterday, was that beta I, it was a gradient of something, and so I could eliminate. But of course, that's a gauge statement.
And there are no zeta dot terms which will appear in this relation.
There will be zeta dot for sure, but then you check that those are basically suppressed by slow roll, if you want, and then they go to 0. I mean, they are a leading order. It's a very small motion, no? So you know that when you have radiation, we are talking about adiabatic modes, so zeta dot, both in slow roll inflation and in radiation, it's roughly 0. I mean, it's not 0, obviously, but it's slow roll suppressed. Okay, so this is right. So this is what is happening. Okay, so then at super horizon scale, that's why your point is correct. So why here we don't get time derivatives or something? Because we do, but those time derivatives at super horizon scale are actually suppressed by slow roll parameters. Okay, which is why actually we can use the whole perturbation theory, as you said yesterday, and we transport it directly to radiation, because the curvature perturbation is constant there and constant there, so it's simply, we can simply transfer by a factor, what was 5 divided by 10, no, 5 divided by 9, or something like this. 9 by, okay, all right. Okay, so if we do that, then at super horizon scale, as we said, we have a kind of generalization of the Poisson equation, but completely nonlinear. Okay, so as you can see, even if zeta is Gaussian, delta rho is far from being Gaussian. Right? Because it's an exponential of a Gaussian. It's even more complicated than an exponential of a Gaussian. Okay, depends also on the derivatives and all these kind of things. Okay. So delta rho over rho is not Gaussian, and it's a monster. Okay? Statistically, this guy is a monster. But fortunately, we are not going to deal with this monster. We are going to deal with the compaction function, and some magic will happen now. So, well, remember that in that metric, also the area radius now is simply equal to R A E to the zeta, right? So you can see here, I can write in spherical coordinates. Okay, so the area radius in this coordinate zeta, it's simply that. Okay. Okay, so the magic is the following, that now we don't need to calculate delta rho over rho, but what we have to do, we want to calculate the compaction function, okay, which is this expression there. Now, you can see immediately that something like the Gauss law, the Gauss theorem for integrals appear, right? Because it's a Laplacian integrated over a volume. Okay, so you can do a little bit of algebra, and then delta rho over rho. So rho bar, of course, is following the Hubble equation. Okay, so rho bar is simply h squared divided by 3, okay, in these units. And so if you plug this into the compaction function, what you get magically, well, I say magically, but in fact you calculate it, so it's not magical. But it's, let's say, it's quite impressive that on this monster, what you get is 1 minus 1 plus. We are in spherical coordinate now. That's it. So the magic is that even if delta rho over rho is exponentially complicated, because it's a statistics that is related to the exponential of zeta, the compaction function, this is the object that we want to, that we care, is actually only quadratic in zeta. So if zeta is Gaussian, that's very simple. This is a chi-square distribution. Okay? So this whole complication, and this is fully nonlinear, it simply comes into a chi-square distribution. Yeah. Prime is derivative with respect to r, like I did it in r prime there. Right? So zeta prime is d zeta dr. Okay? So what I'm doing is I'm assuming here spherical symmetry because I'm considering an isolated perturbation. We're going to check this indeed is spherical statistically. So this is minus dt square plus r square, plus e to the 2 zeta a square multiplied by dr square plus r square d omega square. Okay, in spherical symmetry. Simply dx in spherical symmetry.
Expanding universe, you have a spherically symmetric over density.
Exactly. So it's almost, it will never be exactly because even if you have a perturbation, you will always have more than one perturbation. So the other perturbation will be far away and very small. So it will a little bit interfere. But let's say with a very good approximation, your perturbation is going to be spherical. So under this approximation that we consider an isolated large overdensity, okay, around this R means that I pick the center of my perturbation and I consider the radius around this peak, okay, of the perturbation. Yeah, is that clear? So if you want, in fact, this is what we'll need later on. The idea is the following, that we have a large perturbation in a point x con 0, which I pick in space. Okay, so the space is homogeneous isotropic. There will be some point, let me call it x con 0, in which I have a very large perturbation. Okay, and then around there, I can define a radius, which is obviously minus x minus x con 0, and the metric is invariant under rotation on this displacement, okay, with respect to x con 0. So that's the idea. Okay. Now, another thing that is very interesting is the following, that the compaction function, as we defined here, it was in principle time dependent. Okay, so I never told you that the compaction function is time independent. But once we plug into the metric, we find that actually the compaction function at super horizon scale is constant. So it's frozen like curvature perturbations. This is very helpful. Why is very helpful? Because I don't need to fix any slice on time to give you my probability distribution. Because as long as I take initial conditions that are super horizon scale, those have the same probability distribution. Yeah, because it doesn't change in time. Okay? So what is going to happen now is that what you are going to see, what I need to give you is initial condition for this compaction function, then the universe will expand, and so all perturbation will re-enter the horizon and start to evolve. When they start to evolve, the compaction function that was smaller than 1 start to grow for certain initial condition, get to 1, form a trap horizon, and start to collapse. And then accretion, and so far so on, and form a black hole. Okay, so that's more or less the physics. Yeah.
So the time dependence of the compaction function is only in the curvature equation, right?
Yeah, at that moment there is no time dependence.
Yeah, that's constant. So I mean, when it re-enters the horizon.
When it re-enters, of course, you have only one. When it re-enters the horizon, you have the evolution of the radiation, so the expansion of the universe, so the evolution of the curvature, which is a completely nonlinear system. Now we are not doing perturbation theory. We are really doing full numerical relativity. Okay, so we are forming a black hole. So this is a complicated interaction between how the perturbation evolve and how the universe expands. Okay? So, but this is fully fully time dependent when it enters the horizon. But what we prove is that this object at super horizon instead is time independent. So that's the good thing. Okay, which is similar to what we do in CMB. In CMB, we take initial condition at super horizon scale because everything is constant, and then but the CMB is small fluctuation. So then after it's very easy. We don't need numerical relativity. I mean, to do CMB, we just need the perturbation theory because the fluctuations are small, and so we evolve inside the horizon with perturbation theory. However, here we cannot because the system is completely non-perturbative. Okay. So far, so I need to give you some recipe. Either you come with your code, or I need to give you some recipe to know what are the initial conditions that give you that eventually will form a black hole. Okay. Now let's do a simple mathematical trick to rewrite actually this object there in a slightly different form. Okay. So what we need for the compaction function is R derivative of zeta, right? So this is the object that we need inside the compaction function. And now we notice the following. Let me take a ball, okay, of radius r. Okay, I take a ball of radius r, and I'm integrating in this ball the Laplacian of zeta. Okay. Again, this is Gauss law, okay, for integrals. So this is simple in spherical symmetry. So this is simply 4 pi r square zeta prime on. So I'm taking a ball centered in 0. So what this guy will depend on is r. This is the radius of the ball, okay, and depends on where I center the ball. Let me call it x con 0. Okay? So I take a ball, and then what I'm doing is what is called in large-scale structure is smoothing the perturbation over a ball of radius r. Okay, so I'm doing this integral. So then what happens is that, of course, I can revert, and I can say that, well, instead of calculating r zeta prime, I better consider actually this integral. The reason is that this integral will be connected to the Fourier decomposition. So we'll see in a second. Okay, but up to now, that's okay. No? So this is a simple mathematical statement. Okay. So okay. Right. So then, of course, I mean, this is simple. R zeta prime, it's simply equal to 1 over 4 pi r, the integral over a ball. Then now let me write in this form, Laplacian squared zeta, and I put a theta function of r minus x con 0. Okay, that's precisely the same thing. Okay? So it's integrating over a ball. This is in spherical symmetry. It's simply I'm doing this integral with cutting at the size of the ball. Okay? And now let's consider, because what we say is that we are interested. We know the statistic of the Fourier modes of zeta. So what I want to do now, I want to replace, instead of zeta in this integral, I want to replace the Fourier modes. Okay, that's the thing, which again, I remind, it's just the integral d3k over 2 pi to the cube e to the I k x zeta k. Okay. And so now what happens is that if you plug this one here and you exchange the integral, instead of the integral in k before, you do the integral in r. Okay, so basically you get something that is an integral in k, because that's what is left over. Okay, so I leave you doing this little exercise. So just put this one there and integrate in x, okay, in spherical symmetry. And then what you get And then what you get is this, that r zeta prime is equal to 1/3 the integral of d3k over 2 pi to the cube e to the I k x con 0, which is the center of our ball, okay, kr to the power 2 zeta k wth of kr. Now this guy here, it's basically the Fourier transformation of the theta function. So this guy has the following form: 3 sine of kr minus kr cosine of kr divided by kr to the cube. Okay. So now, pretty cool, because this function that we need for the compaction function is written in terms of the Fourier modes of our curvature perturbations, okay, which we know the statistics. Okay, so it's very important this. Okay, so then to simplify the way of writing the compaction function, so let me erase here. I just define a new function gr of x con 0, so which depends on the radius of the ball and the center of this ball, which is nothing else than, well, simply I put a factor r zeta prime. And why do I do that? I'll explain you in a second. And this is minus 4 divided by 9 integral of, well, what is written there? d3k divided by 2 pi to the cube kr square zeta k wth of kr. Now I'm doing this because, fun enough, precisely this combination, okay, as you can see, how did I get this? I get it from an integral of the Laplacian of zeta. But the Laplacian of zeta is precisely what you would think of linear perturbation theory that relates the gravitational potential to the overdensity. And the factor minus 4,3, in fact, is precisely what we call the delta rho over rho linear. Okay. It just happened to be that, I mean, just by chance, that actually the compaction function, which is a completely nonlinear system, it depends in structure from the linear overdensity, smoothed on a sphere. Okay, because simply it's Laplacian of zeta instead of the complication that we had before with all the Laplacian of exponential of zeta. Okay. So this is just an historical way to write, but with that, what we can, so the factor minus 4,3 of course is not going to change much on our life, so, but just for fun to make a connection, because we have some kind of physical understanding of linear perturbation theory, okay? But this is, I insist, is fully nonlinear. How are we going with time? Because I don't have my, okay. So I have half an hour, no? Yeah. All right, so by defining then this G, so I simply rewrite, and this will be our starting point, the compaction function, which is a function of R x0, where x0 now is the center of our perturbation, because we say spherically symmetric around this center. Okay, so I'm picking us in a space this center, and is a function of, so you can rewrite a gr x con 0 1 minus 3 divided by 8 gr x con 0. Okay, so that's the compaction function, which is this object that will give us the initial condition for our evolution into a black hole. Okay, so obviously, because G was G is actually a multivariate Gaussian distribution. C is a multivariate chi-square distribution. Okay, and now let's see what we want to do with this thing. So let's think. What we want to know is something that we call threshold. Yeah.
Just a quick. This is just the same expression you wrote earlier in terms of R's
Yeah.
prime, right?
Yeah.
1 minus 1 plus R's.
Yeah. It's exactly the same because I'm just rewriting this in terms of this Laplacian, and which is, so R zeta prime is precisely this, and then what I wrote before was 1 plus R zeta prime square. I simply expanded the square, and then I use this factor minus 4(3) because it's for fun. It's related to the linear over density. Otherwise, we will fluctuate around some 3 divided by 4, and that's it. So then we have this. So basically, what happens is that if you want, the compaction function is related to the smoothed linear over density. Okay. All right. If we go for G small, no. So for G small, this doesn't exist. Linear perturbation theory, so it's simply G. Okay. Okay. So as we said, the compaction function is our gravitational potential. Okay. So what we want to know is a value for this compaction function that given initially, such that at some point we will form a black hole. Now, what we need to give is what we call a threshold. What is a threshold? A threshold, it's something that we say that, well, if I'm slightly higher than that, I'm gonna form a black hole. If I'm slightly lower than that, I'm not gonna form a black hole. Okay, so I need that value, that numerical value. When I am at the threshold, what do I form? Well, what do I form at the threshold is what we call a virtual black hole. What is a virtual black hole? Basically, it's black hole of mass 0. So it's kind of a very strange thing, but what it means is that if I take exactly at the threshold, I will basically neither form or form a black hole. Okay, so because of course quantum mechanically this point doesn't exist, so I'm either a little bit higher or a little bit lower. So I either just dissipate away because the universe expands, or if I am a little bit higher, I form a black hole of very small mass. So what we said is that at the threshold, we form a black hole but of mass 0. Okay, so that's a very weird definition, but that's what we would call threshold. Okay, so it means that at slightly higher, I would form a black hole of mass different from 0. Okay. Okay, so but these make you think, okay? Because what happens is the following. Now, by regularity, what we have to have is that the gravitational potential at R going to 0, it has to be 0, otherwise it will be an explosion, okay? So the compaction function should go to 0, and of course also at infinity, the compaction function should go to 0, okay? So, but what I want is that, of course, I want to form a black hole. So if it is always 0, then it's not going to form a black hole. So I need to have something larger than 0. That means that there is at least a maximum. Okay? And in fact, I mean, more than a maximum will be completely statistically improbable. So let's work with one maximum. Okay? So the compaction function is an object, and whatever it is, will have certain shape, but it's going to 0. So this is in R. This compaction function has a maximum and then goes to 0 at infinity. Okay? So where do you think I should calculate the threshold then? So the threshold is, as we said, it's the moment in which I form a black hole of mass 0. So that means that basically there is only a very thin shell that wants to collapse. Anything else is dissipated away. Okay? So that the point in which the first point that would want to collapse would be, of course, the point of highest gravitational potential. Okay? So what I'm gonna do, I'm gonna define the threshold at the maximum of the compaction function. So what we'll want to know is the value of the maximum of the compaction function such that if I go slightly higher, I will form a black hole of mass different from 0. If I'm exactly at the threshold, I form a black hole of mass 0. This is, of course, is a mathematical statement. I don't form any black holes, right? Because it has mass 0.
So this limits small r going to 0 and infinity is fine.
Yeah.
But this would always correspond to capital R going to 0 as well. That was a product.
Sure, because you are in spherical symmetry, and if it doesn't, so you will get some divergences in Riemann tensor, for example, or whatever. I mean, you will get singularity. So here is all smooth, the space-time.
There's an A of t also, right, in that definition.
Yeah, but the A of t, it's a scale factor, depends on time. So, of course, if you go back at the beginning of the universe, at the singularity, if there was one, if there was inflation, there was none. But otherwise, take it as a constant. So it's something, right? So it's R-E-Z-A, right? So this guy, you take it as a constant. We are not going in A going to 0. Of course, this will be the cosmological singularity. But this guy here is regular in 0. Okay? And so, and at infinity, of course, as well, because the perturbation at infinity has to be basically 0 by boundary conditions. Okay? So then my threshold is given at this. So what I would call threshold would be some number such that the compaction function at the value r equal to Rm, given the peak of the overdensity, is bigger than certain value that I call C critical. Okay? So if that happens, I will form a black hole. Okay? So this is just, I didn't tell you yet which one is the threshold, but that's the concept. Okay? I have to give you some value for this compaction function at its maximum. Okay, so now this is, in principle, is a complicated problem of general relativity. So because what I'm telling you is, okay, so I give you some initial distribution of my gravitational potential. I give you the value at its maximum. So I give you, if you want, the shape of this distribution and the value here. I give it to you. You go home. You take your favorite numerical relativity software. You start evolving from there, and you check whether this value I give you form a black hole or no. In fact, you will come to me and say, no, look, you have to take that number, not this other number. Okay? So in principle, that's what we should do, right? And in fact, this historically, that was what people did, especially the guy that wrote the first codes for this in spherical symmetry was Ilya Musko. So the paper, the last paper, it's a PRD 2019. And so what he showed is that basically the threshold, so the value of the compaction function that you have to give at this maximum, depends on the full shape of your gravitational potential. So it doesn't depend only on that point. Okay. So in fact, it depends on a radius that goes from 0 to Rm a little bit larger, let's say. Okay, so slightly more. Okay, so what happened after is not really important. Why? Because we are talking about threshold, and then what happened after is basically will be dissipated away, because otherwise it will form a black hole of mass non-zero. The threshold is mass 0. Okay. And so this can be solved with a system that is called was given in the 50s, 60s, I don't know. Misner, Sharp, Hernandez system, which is basically the full numerical relativity of gravitational collapse of spherical object in a Friedmann-Robertson Walker. So they give you the equation, and that is where they define, by the way, the Misner-Sharp mass. So in that paper is the definition. Okay. And so in principle, if you want to know the threshold exactly, you cannot do anything else than solving numerically. But this will be a complete disaster. Why would be a complete disaster? Because now, if I have to provide you a statistics to know how many black holes are in the universe, that would mean that for each random fluctuation, you have to do a simulation. Imagine, you have to do infinite simulations, and then we draw the distribution of our initial condition that would form a black hole. This is a disaster because we'll not have the whole time in the universe to do that. Okay, so we need to find a way out to that. Okay, and that's where we actually found an analytical method to get this threshold without using numerical relativity. Okay, so that was the cracking point to really do the statistic of primordial black holes. Okay, so let's see. Yeah, here. Oh. Okay, so before, so there's a question? Okay. You can ask, yes.
So there is a model for collapse to a black hole in an expanding universe. This business Fernandez.
Well, there are the equations, but you have to solve it numerically because they depend. So the evolution depends on the full profile of your initial condition for the overdensity. So it's not you cannot find analytical solution, principle. So there are no known analytical. So it's really a numerical relativity problem. Although it's a one-dimensional general relativity because it's just a two-dimensional time and radius, but it's fully nonlinear, so it's not linear perturbation theory. So you can imagine that. Well, for dust, of course, there is a solution. We all know Oppenheimer-Snyder, but that's not dust. So this is radiation, and for radiation, is enormously complicated because you can imagine that you have to fight the pressure of radiation and the expansion of the universe against the gravitational collapse. It's a completely nonlinear system. Okay. For dust, of course, there is a solution, but that's not what we want. Here we are in radiation. Okay. So there is no solution. Well, there's no analytical solution.
You do construct solutions inside neutron stars and so on, right?
But this is static.
Sorry?
This is static. So you mean it's a static and not even in flat space. So this is a collapse into a black hole in a Friedmann-Roberts-Walker universe. Which paper? Depends on which paper. They wrote billions of papers.
I know the earlier paper, 2013, I believe.
Where they gave the threshold.
Right.
It's completely wrong. So, well, it's completely wrong, and in fact, it doesn't. You can check that this doesn't even make sense because when they get that, when the equation of state, for example, is large between pressure and energy density, with that formula, you get that it's easier to form a black hole. It completely makes no sense because pressure is larger. So it's I mean, it was an initial way trying to get a threshold with a very schematic model. But this model is completely realistic, and in fact, at the end, it is valid only for dust. But for dust, it's trivial. So the threshold that they found is completely wrong. Okay. Well, this was proven in different papers. I mean, it's even with all the numerical simulation. For example, in Musco, he showed that all these thresholds were no sense. Okay. All right, so then the thing is that where we actually we found a way out to the numerical relativity was in this paper. And it is purely 2020. Okay, so this was really the moment in which we could have started doing statistic of primordial black holes. We will give the threshold of primordial black hole analytically. Okay? Before showing you this, what we have done this, let's make a pause 1 second and look again at the form of the compaction function. So the compaction function, I remind you, it was this quadratic form minus 3 divided by 8 gr of x con 0, right? So this was the compaction function. Now this is, so if you see the structure of C in terms of G, this is gone to 0 and then has a maximum and then goes down. Okay, so this is perhaps. So this is an easy exercise, right? You take the derivative in G and you find the maximum. It's, even my kids can do that. So C, and then this is in terms of G. This has kind of parabola, inverted parabola, okay? And it has a maximum here at the value which is 4/3. All right, so of course those. So we divide, let's say, the region of the compaction function in terms of region 1 and region 2. So this region 1 is where the compaction function grows by growing the linear perturbation theory, and the other part, which is very funny, decays, so the gravitational potential decays by growing the linear perturbation theory. So this part here is very funny, and it's called, it generates what they are called type 2 black holes. And this region here, so if your threshold is within this region, is what we call type 1 black holes. Now, type 1 black holes have all the intuition we had so far. Type 2 black holes have this funny thing, that if we increase the linear over density, we decrease the gravitational potential. So they have to be treated separately, and I'm not gonna do them in this course, because it's still an open question of what is going on. Nevertheless, they are kind of insignificant. Why? Because already to get a large overdensity is a rare event, okay? So imagine if I want to have even larger overdensity, okay? Then it will be even more exponentially suppressed. Okay? So the domination of black holes is in this region, which is called type 1. Okay? So for this course, we will talk only about type 1 black holes. Okay? Type 1 black holes are what we would imagine, because, for example, a maximum in the compaction function. So now you see that all derivatives match, because if we take the maximum of the compaction function, this will be a gradient. Okay? Is also a gradient of G, if we are on this side. If we are that side, no, because it swapped the sign. Sorry, for the second derivative, of course.
I have another question.
Yeah.
The G depends only on zeta k.
Sure.
What we typically know is zeta is the power spectrum.
Sure.
So
I'm gonna go there, yes.
okay.
Yes, yes.
Because
For now, it's zeta k is a random variable.
Zeta is just some random.
It's a random variable. I mean, it's the Fourier transformation of a curvature of perturbation. It's a random variable. We have to connect, of course, to the power spectrum. We didn't do it yet. Okay? So for now, we did that. By the way, in this thing, of course, I kind of made. I was too quick because, of course, here there is e to the I k x con 0. But once you find the peak, you can always shift your coordinate to take this equal to 0. Okay, so you just take the center. Okay. Yeah. But in principle, that depends. Of course, there is still this exponential e to the I k x con 0. Okay, so, but a posteriori, once you find the peak, you can put it equal to 0. It's simply a shift of coordinate. You take your coordinate, you fix it there. Okay. All right. Okay. So then, what? Sure. Yeah, go ahead.
So we have a spherical symmetry, right?
Yes.
But then if I have to relate to zeta k, which is primordial,
Yes.
that may have a different structure as zeta.
I'm gonna go there. I'm gonna prove that it's spherical. So for now, I just use our physical intuition to go ahead, to not stop with the mathematics that we'll do later. But our physical intuition is that I have an isolated large fluctuation, then it's spherical around that large value because of scalar field. Okay, because scalar field doesn't have any direction; it's isotropic. But I didn't prove.
One more probably question. Where have we assumed it is sub-Hubble?
This is super Hubble. I never use sub-Hubble yet. This is all super Hubble scale. So I'm giving you the initial condition of the compaction function at super horizon scale. Okay, so I will not give you initial condition at sub-horizon scale. Why? Because at sub-horizon scale, everything is fully dynamical, and I cannot give you a statistic. Because the statistics will only be given by Fourier modes. But these Fourier modes also depend non-linearly in time. It will be impossible. I mean, this would be non-Gaussian for sure. I mean, it would be something crazy. Okay. So it's in the spirit of inflation, even for radiation, for the ZMB, to give you the initial condition at super horizon scale. Yeah. Okay, so then what we are going to consider are only the cases of which the threshold GR x con 0 is smaller than 4/3. So we are in type 1 black holes. Okay? When I say that this is statistically improbable, what happens is the following, that G itself also is a multivariate Gaussian distribution. This is an integral of zeta. Okay? So also for zeta, the only interesting numbers is its mean value and its variance. Okay? So when I say that this is improbable, what I mean is that GR x con 0 divided by the square root of the two-point correlation function grx con 0, grx con 0. Okay, this is in real space. This is much smaller than 1. Okay, so that's why it's improbable, because this is a Gaussian variable, but what is really in the Gaussian distribution is the variable divided by its variance. No? So this goes like e to the minus x squared divided by sigma squared. Right? So the important object is this, not x itself. And so, sorry, the other way around, of course. I want to have yeah, sorry, I'm interested in this much bigger than 1. So meaning that larger it is, more exponentially suppress this. Okay, because it's this guy. So larger is this guy, larger is the exponential suppression. Okay, so this is less and less improbable going in that direction. Okay. Okay. Okay, so if we are in type 1, then black holes, what I was saying is that everything looks like a bit easier, because basically the maximum of the compaction function correspond to the maximum of G, right? Because when I take the second derivative, the parenthesis doesn't swap sign. Okay, so then I can, instead of, for type 1 black holes, it is actually equivalent to consider the statistics of G instead of the statistic of C. So you can imagine there is a huge simplification, because instead of going to a chi-square distribution, I just look directly to a Gaussian distribution. Okay? Because what I want to know is, first of all, I want to know the condition for which the compaction function has a maximum, which is the first derivative equal to 0, and the second derivative less than 0 at that point, right? So that's the definition of maximum. But this is if and only if for type 1 the Rg is equal to 0 and the second Rg is less than 0. Okay, so I can work directly with G. Okay, so that's a simplification. Now we need, nevertheless, I was kind of lying you that we don't need any input from numerical relativity because we need some. Okay, so one input that we need to know is the mass of the black hole. Okay, why? Because at the end, what I want to know the density of black holes with respect to the density of radiation, for example. And to know the density of black hole, I cannot simply count the number of black holes. I have to also give you the mass. Okay, because that would be the energy density. And so now, at the threshold, as we said, we form a black hole of mass 0. What does it mean, really? So it means that this gravitational potential, so we have a gravitational potential, maximum gravitational potential that re-enter the horizon to then evolve and try to form a black hole. How much mass does he have for himself? Well, in principle, it has all the volume of the universe in that moment. Okay? But of course, it's not going to eat up all the universe because it depends on how large was his gravitational potential. So it will only eat up some fraction of it. Okay, so what one finds then is that the mass of the black hole, and this you can check numerically, so you do your numerical relativity code, it's equal to some constant that weakly depends on your gravitational potential. So that, and this is the only unknown factor, but is a factor of order 1, so it's not very important with all these exponential that we run around, divided by basically the mass that you would have when your fluctuation of size Rm re-enter the horizon. So it's basically the Hubble radius. Okay, so you will have all the volume of the universe. This will give you all the volume. And then this will depend on how far you will be from what we would call the threshold. With a scaling law that is actually so this is a self-similar collapse, if someone of you knows. So this was discovered by Choptwig with scalar fluctuation, that basically when you try to form a black hole with scalar, you will get this self-similar solution, which is some function minus a critical to some critical exponent that is universal. And what happens is that it happens the same also for black holes formation in radiation. And the critical exponent is 0.36. Okay, so this is a numerical result. Okay, so this is as far as you are not too far from the critical value. Okay, so but if you are close to the critical value, which is what we are interested in, because it's more and more improbable to go far away from the critical value, the critical value is very improbable, then this is the mass of your black hole. Okay, so it's the full mass of the universe that you would have in your hands, but you only eat up a portion. That depends on your distance from the critical scaling. Okay, so this is the input that we need from numerical relativity. What is this HRM? As I said, it's the Hubble scale when the wavelength of radius Rm enters the horizon. So this is basically 1 over A at some value in time Rm. Okay, so when this is equal to that, so this define this value there. And the scale factor, we know we are in radiation, so this goes like 1 over A to the 4. So you do a little bit of algebra and you get HRM, okay, which is actually proportional to R squared. Okay, so but the system is closed, so you can do that. Okay, so this is, of course, this is the weird unit I'm using because you don't see this is a mass, but it is a mass, because if I now replace Planck's units, the mass associated to the horizon, which we call it m horizon, is basically m Planck square divided by h when the scale crosses the horizon. So if when we replace, this is a mass, okay, when we replace the unit. Yeah? Okay. And then we get what I promised, that when the compaction function is equal to its critical value, we form a black hole of a mass 0. Okay, so that's the idea. Okay, so I don't think I can do much more today, but so tomorrow what I'm gonna show you is actually how to, instead of using numerical relativity to find this point, this critical value, to use a completely analytical estimation that incredibly, I would say remarkably, is correct up to few percent with respect to full numerical relativity. This is enough. Okay? It's enough for all possible application we want to do. And then what I'll show you is that until now we just said physically that the system is spherically symmetric, but tomorrow we are going to prove statistically that indeed the most probable configuration of our perturbation is spherically symmetric. Okay, so not only our physical intuition is correct, but mathematically we can prove. Okay, and then I'll finish by finally discussing the statistic of primordial black hole, which is basically the statistic of initial condition of this compaction function. Then we can count how many black hole will be formed in the universe, given some power spectrum. Okay, so that's the idea. All right, I stop here then.
So how does it work with, so you said that you need the input from numerical relativity to find the mass, right? But I imagine the code gives you a number for the mass. So are you fitting it to some function or something?
Well, it's not. Yeah. So basically, you move your initial value of the compaction. You need initial profile of the compaction function. So this is a function m dot that depends, of course, on where you put your maximum of the compaction function, and will depend on the value of the compaction function in principle at all points. So you give me a profile. And sorry, this is, maybe it was slightly misleading. So this is C at Rn, okay, at the maximum. Is the value at the maximum. So it's the threshold. So you give me this value, and then you give me a different profile. Okay, because you are not at the threshold. I mean, you are forming a black hole, so you are larger. Okay, and then I'll give you numerically the mass. Did that answer your question?
My question is, how do you know to follow that specific?
Because you check different profiles. So you take different initial profiles.
Yeah,
It's going to give you different mass, but then you put in a logarithmic scale, you see that it's a straight line. Okay, so you basically see that if you do a plot of mass with respect to log of C minus C critical, this is, I mean, all the points lie in a straight line. That's the same thing of the Chopwick result. Chopwick. I never can say. Someone can say for me. Chopwick. No, numerically. No, those are all proof that are done numerically. Also for primordial, for scalar field and for primordial black hole as well. So for spherically symmetric cases, gravitational collapse of spherically symmetric case still follow self-similar solutions. Okay, that's a numerical proof. You have to use your code and do it, brute force. As far as I know, there is no really analytical proof of that. Not even for the scalar field. Or I don't know if someone knows, but as far as I know, it's all numerical. I mean, there are some reasonings, of course, but the analytical proof that this should be a self-similar solution, I don't think is there. Okay.
Any other question for Cristiano? Okay, let's thank Cristiano.
Okay.
Okay.
Thank you.